It's a Spotify podcast.
You pushed me down, thought I'd stay on the ground, counting me.
Hey everyone, welcome to another episode of Rabbit Holes Deep Dive. This is where we take just general topics and dive deeper into them. Sometimes it's what Steve and I talk about, or Miranda and I talk about, and or one of you guys put it in the comments below, and we'll dive into it. Can't wait. So this episode is when AI becomes a body. The race to turn intelligence into labor. A robot walks into a stage. It balances on two legs. It turns, it punches, it dances, it recovers after being pushed. The video spreads across the internet. Millions of people watch. Some see the future. Some see a toy. Some see a threat. Some see a machine performing a carefully rehearsed routine in a controlled environment. And all of them may be right, because there are really two humanoid robot stories unfolding at the same time. The first is visible. It is the story of machines that run, jump, dance, and imitate human movement. The second is much harder to see. It is a story of machines that run, jump, dance, imitate human movement. The second is much harder to see. It's happening inside factories, investment prospectus, government industrial plans, training facilities, simulation systems, semiconductor supply chains, regulatory agencies, and warehouses filled with machines, repeating the same physical action thousands of times so that an artificial intelligence system can learn what a human child begins learning almost immediately. How the physical world works. On August 6, 2026, Chinese robotics company Unitree priced its initial public offering in the Shanghai at a valuation of approximately $9 billion. That event matters for reasons larger than a company itself. Unitree became the first mainland listed Chinese manufacturer centered on humanoid robots. Its 2025 revenue had grown more than fourfold, and for the first time, humanoid robots generated more revenue for the company than its better established four-legged machines. On the same day, another detail emerged. DeepSeek, the Chinese artificial intelligence commonly known primarily for language models, invested approximately $20.8 million through Unitree's strategic placement. The two companies said they would cooperate in embodied intelligence, the attempt to connect AI systems with machines capable of perceiving and acting in the physical world. At almost the same moment, the United States was moving in the opposite direction. The Federal Communications Commission had expanded restrictions affecting new Chinese numbered and quadrupled robot models, citing national security concerns and the desire to encourage domestic production. Capital, artificial intelligence, manufacturing, robotics, security, trade, data, all converging around machines shaped roughly like us. So the important question is no longer, can we build a robot that walks like a human? We can. The deepest question is, what combination of intelligence, reliability, cost, and experience turns a walking machine into economically useful labor? Because when AI gets a body, it enters a world where words are not enough. A language model can produce an incorrect sentence and try again. A robot can drop a steel component, damage a machine, injure a worker, fall down a staircase, or make a mistake. No training, simulation, predicted. The physical world does not have an undo button. And that is where the rabbit hole begins. The demonstration. Humanoid robots create an immediate psychological reaction. They look enough like us that we instinctively interpret their movements as signs of intention. A machine turns its head. We imagine attention. It reaches toward an object. We imagine purpose. It stumbles and recovers. We imagine determination. This is one reason humanoid robot videos are so effective. The body communicates a story before the technology is explained. A wheeled individual machine moving a box may appear ordinary. A human-shaped robot moving the same box can look like history arrived, but appearance can be misleading. A demonstration may be fully autonomous, partly autonomous, teleoperated by a human, based on pre-recorded motion sequence, restricted to a carefully mapped environment, supported by off-camera equipment, or assembled from several successful attempts. These distinctions are not always obvious from the final video. That does not mean the demonstration is fake. A machine capable of excluding a difficult motion is still an engineering achievement. But motion is not the same thing as useful autonomy. And useful autonomy is not the same thing as reliable commercial work. A humanoid may perform a backflip yet fail to sort unfamiliar objects on a cluttered table. It may run across a laboratory while struggling to open a flexible plastic package. It may lift a heavy container but be unable to recognize that the container is damaged. It may repeat one task impressively and fail when the lighting, floor, surface, object, position, or workflow changes. This is the first major lesson of embodied AI. Physical intelligence is not one capability. It is a stack: perception, balance, navigation, object recognition, grasping, forecast, control, planning, memory, safety, language, understanding, social awareness, and the ability to recover when reliability refuses to match the plan. Humans combine these capabilities and abilities so naturally that we underestimate their complexity. We walk through a room without calculating every root placement consciously. We pick up an unfamiliar cup while adjusting the pressure so we do not crush a drop of it. We recognize that a towel behaves differently from a hammer. We anticipate that an object may slide, bend, or spill or break. We understand that a person stepping into our path is not merely a moving obstacle. A robot must somehow acquire comparable physical judgment, and it must do so consistently enough that someone is willing to employ it. Why a human body? The humanoid design creates an obvious question. Why build a robot shaped like a person at all? Wheels are usually more efficient than legs. Fixed industrial arms can be faster, stronger, and more accurate than human arms. Specialized machines already wield vehicles, move pallets, harvest crops, inspect pipelines, and assemble electronics. If the goal is to automate, why recreate the human body? The strongest answer is not that human body is mechanically perfect. It is that the human world was constructed around it. Door handles are placed at hand height. Stairs assume legs. Shelves assume human reach, tools assume hands, vehicles assume human proportions, warehouses, hospitals, kitchens, factories, and homes contain infrastructure built for bodies like ours. A machine shaped roughly like a human may therefore operate in existing environments without forcing society to redesign everything around the robot. That is the promise. Instead of building a new automated facility for every task, build one machine capable of using the facility already there. One body, many jobs. In theory, but phrases in theory carries almost the entire weight of the industry, because a general purpose body is vulnerable only if it develops general purpose competence. Otherwise, the humanoid form can become an expensive compromise, more complicated than a wheeled platform, less efficient than a specialized machine, harder to stabilize, harder to maintain, and still incapable of adapting to unfamiliar work. The humanoid robot is therefore a bet, not merely on hardware, on generalization, the new revenue system. Until recently, much of the humanoid robot industry was evaluated through demonstrations, prototypes, and investment announcements. Unitree's public listing introduces a different kind of evidence, financial disclosure. According to Reuters, Unitree's revenue exceeded 1.7 billion yen in 2025, more than 4 times the previous year's level. Humanoid's products produced approximately 867.8 million yen in revenue, surpassing the company's quadrupled business. That does not prove that humanoids are already replacing large numbers of workers. Revenue can come from universities, research laboratories, government agencies, technology companies, demonstration programs, developers, education, entertainment, and experimental developments. A robot sold is not necessarily a robot performing profitable autonomous labor. But the figures do establish something important. Humanoid robots are no longer only research prototypes supported by speculative venture capital. They have become so meaningful commercial products category for at least one major manufacturer. That is a signal, not proof of the final destination, a signal that the infrastructure of an industry is beginning to form. Factories, supply chains, customers, service networks, capital markets, and competitors seeking lower prices. The price difference is especially important. Historically, advanced humanoid robots were extraordinarily expensive research systems. Unitree helped expand attention by entering a smaller humanoid platform at prices far below traditional laboratory machines. Lower prices allow more universities, developers, and companies to experiment. More machines produce more experience. More experience produces more data, and data may be the resource the field needs most. The missing childhood. A language model learns from text, images, audio, code, video. The internet provides enormous quantities of those materials. Robots face a different problem. The internet does not contain enough structured examples of what it feels to pick up a slippery object. How much force a gripper should apply. What happens when a box shifts unexpectedly? How a human coworker reacts when surprised. how a door sticks during humid weather, how fabric folds, how cables tangle, how objects behave when damaged. Video can show what happened, but video alone does not always reveal the forces, contact points, failed attempts, and motor decisions required to reproduce the action. A robot needs experience connected to action. It needs to know not only what the world looks like, but what happens when it intervenes. Push here, lift here, rotate this, step there, apply the less pressure, stop, try again. Human beings spend years collecting this type of physical data. We call it childhood. A robot company must manufacture it. That may be the hidden bottleneck behind embodied intelligence. Computers describe the need for large quantities of physical world training data as one of the central challenges facing Unity and DeepSeek's collaboration. Unity has been gathered information through trials in which humans guide robots through actions, producing examples the machines may later learn to perform with greater autonomy. This creates an unusual paradox. The dream is autonomous labor, but the plan to autonomy may depend on large amounts of human labor. People teleoperate robots, correct their movements, label failures, reset environments, repair machines, demonstrate tasks, review recordings, and decide whether an action was successful. Before robots can replace labor, labor may have to teach them how. Cooperation, cheating, or training. When viewers discover that a humanoid demonstration involved human teleoperation, the response is often immediate. The robot did not really do it. But that conclusion is too simple. Teleoperation can serve several legitimate functions. It allows a machine to perform useful work while autonomy remains incomplete. It lets human operators intervene when a robot becomes confused. It produces a demonstration from which AI models can learn. It can provide safety supervision, and it may create a gradual path from full human control to partial autonomy and eventually more independent operation. The better analogy may be aviation. Modern aircraft contain extensive automation, but human pilots remain available to supervise, interpret, and respond. And it may create a gradual path from full human control to partial autonomy and eventually more independent operation. The better analogy would be aviation. Modern aircraft contain extensive automation, but human pilots remain available to supervise, interpret, and respond. The presence of a person does not mean the technology is meaningless. It tells us where autonomy ends. The critical issue is transparency. Was the task autonomous? But human pilots remain available to supervise, interpret, and respond. The presence of a person does not mean that technology is meaningless. It tells us where autonomy ends. The critical issue is transparency. How often did a human intervene? How many failures occurred? What happened outside the edited video? How long could the system operate without assistance? What happened when the environment changed? Those numbers matter more than Naomi, cut that. Those numbers matter more than spectacle. A robot that competes completes 90% of tasks may look impressive. In a commercial environment, the remaining 10% can determine whether it is useful. If a human must rescue the machine every few minutes, the robot may not reduce labor at all. It may simply move labor from one factory floor to a remote control station. That could still create value. One skilled operator might eventually supervise several robots. Dangerous tasks might be performed remotely. Workers with physical disabilities might control machines in environments they could not otherwise enter. But this is not the same future as fully autonomous humanoids. The distinction matters for investors, workers, regulators, and the public. Simulation in the real world. Collecting experience entirely in the physical world is slow and expensive. Robots fail. Parts wear out. Environments must reset. Failures can damage equipment. So researchers increasingly use simulation. A vertical robot can attempt the same task as millions of times. It can fail without breaking. Objects can be randomized. Lighting can change. Floor friction can vary. Unexpected disturbances can be introduced. The machine can learn strategies before entering a real facility. NVIDIA and other robotics researchers have increasingly focused on connecting simulation to physical deployment. NVIDIA's 2026 robotics research emphasized the transition from simulated training environments into real-world systems, including data sets and methods intended to reduce the gap between virtual learning and actual operation. That gap is known as the sim-to-real problem. A simulation is always an approximation. Materials behave differently, sensors contain noise, motors have imperfections, objects are scratched, bent, or dirty. People behave unpredictably. A policy that works flawlessly in simulation may fail immediately in real-world warehouse. Researchers tried to overcome this through randomization, increasingly accurate physics, and systems that return real-world failures into simulation for further training. The loop becomes real-world. Simulation, training, real-world test, failure, updated simulation, more training, back to reality. Recent embodied AI research describes this as realize to sim to real cycle. Real sensor conditions inform simulations. Simulations generate large quantities of training data, and trained systems are evaluated again in physical environments. But even sophisticated simulation cannot anticipate everything. Reality contains too many edge cases. This is why a robot working successfully for 1 hour is different from a robot working for 1 year. Reliability is accumulated time, and factories do not purchase demonstrations. They purchase optimum. The factory test. Factories are likely to become one of the earliest serious testing grounds for humanoid robots. The reason is not that factories are simple. They are not. The reason is that they are structured. Lighting is controlled. Workflows repeat. Objects are standardized. Safety zones can be defined. Tasks can be measured. And the economic value of a successful action is often easy to calculate. Move this component. Load this machine. Carry this container. Inspect this part. Repeat. Factories also contain jobs designed around humans. A humanoid machine could theoretically enter these environments without requiring complete redesign. This is why automakers logistics companies, and robotics firms have invested heavily in pilots. But a pilot is not deployment, and deployment is not profitable scale. The gap between those stages is where most robotics narratives become unrealistic. A company may announce that robots are working inside a factory. That could mean several things: a single machine operating under supervision, a limited trial lasting a few weeks, a carefully constrained task, a demonstration during low-risk hours, or a paid commercial deployment producing measurable output. Each represents progress. They are not equivalent. The correct questions are practical. How many robots? How many hours? How many successful task cycles? How much human intervention? What is the failure rate? What is the maintenance cost? How long does the battery last? How quickly can the machine be repaired? What happens when another worker changes the environment? How does the total cost compare with a conveyor belt, a wheeled robot, an industrial arm, or a human employee? Without those answers, factory deployment can hide more than it reveals. The economics of a robot worker. The business case for humanoid labor is often presented through a simple comparison. Human employees earns wages every year. A robot is purchased once. Therefore, the robot eventually becomes cheaper. But this leaves out almost everything. A robot has a purchase price, financing cost, energy cost, maintenance, software, subscriptions, replacement parts, network infrastructure, integration, insurance, supervision, safety systems, downtime, and potentially remote human operators. A machine may also work more hours than a human, but only if charging. Repairs and system failures remain manageable. This leads to one of the most important metrics in robotics: cost per successful task. Not the price of a robot, not the number of joints, not the maximum walking speed. The total cost of reliability completing useful work. A $20,000 robot that requires constant assistance may be more expensive than a $100,000 specialized machine that operates continuously. A humanoid does not need to outperform a human at everything. It needs to create enough value in particular tasks to justify itself. That might happen first in work that is repetitive, ergonomically harmful, difficult to staff, dangerous, or performed in environments where flexibilities matter more than speed. The first widespread humanoid jobs may therefore be less dramatic than public imagination suggests. Moving containers, feeding parts into machines, carrying materials between stations, handling inspection routines, working in hazardous areas. These tasks do not require human-level intelligence. They require reliability. And reliability may be more difficult achievement. The hardware-software divide. The U.S.-China robotics competition is often described through a simple contrast. China has manufacturing scale. The United States has stronger frontier AI. That contrast contains some truth, but reality is more complicated. China has a deep industrial supply chain involving motors, batteries, electronics, sensors, machining, and manufacturing. That can reduce cost and accelerate iteration. American companies benefit from major AI laboratories, semiconductor ecosystems, robotics research, and large pools of investment capital. But robots require both. A brilliant AI system inside an unreliable body is not a useful worker. A low-cost body without sufficient intelligence is not a general-purpose worker. The winner, if there is a single winner, may be the system that integrates mechanical design, actuators, sensors, battery performance, control software, artificial intelligence, training data simulation, manufacturing, repair, and customer operations. This is why DeepSeek's investment in Unitree is symbolically important. That partnership connects a company associated with advanced AI models to a company capable of producing physical machines at scale. The deeper competition is therefore not robot against robot. It is ecosystem against ecosystem. Who can build the machine? Who can train it? Who can produce enough of them? Who can operate them cheaply? Who controls the data? And who can improve the entire stack fastest? The security question. Why would a government restrict imports of humanoid robots? A robot is not merely a mechanical worker. It is a mobile sensor platform. Cameras, microphones, depth sensors, wireless connections, mapping systems, potentially cloud-based AI. A machine operating in a factory could observe facility layouts, equipment production, worker behavior, inventory, security practices, and potentially sensitive industrial technology. A humanoid operating in home could observe something even more intimate. Daily routines, children, conversations, personal belongings, health conditions, locks, entry points, and the physical structure of private life. The FCC's 2026 actions frame certain foreign-made robots as part of a broader national security concern involving connected technologies and domestic industrial capacity. The restrictions affect new Chinese humanoid and quadruple robot models, while critics have questioned the transparency and organization of the policy. The strongest case for restrictions is straightforward. A networked mobile machine with powerful sensors could create espionage, cybersecurity, or infrastructure risk. A foreign government could potentially compel a manufacturer to provide access, software updates, could alter behavior, alter deployment. Supply dependence could become dangerous during a geographical crisis. But there is a serious alternative argument. Security claims can also become industrial policy. Restrictions may protect domestic manufacturers from lower cost foreign competition. But there is a serious alternative argument. Security claims can also become industrial policy. Restrictions may protect domestic manufacturers from lower cost. Foreign comparison. Broadbands can raise prices. Slower experimentation. Fragment technical standards. And encourage retaliation. The question is not whether connected robots create security risks. They clearly can. The question is whether particular restrictions are proportionate, transparent, and based on demonstrable technological threats. Security cannot be evaluated through nationality alone. Domestic robots can also be hacked. Domestic companies can misuse data. Poorly designed systems can create vulnerabilities, regardless of origin. A serious robotic security framework would examine where data is stored, who can access it, whether communication is encrypted, how updates are authenticated, whether operation can continue offline, how sensors are controlled, whether logs can be audited, and what physical actions remain possible after a compromise, because when software controls a body, cybersecurity becomes physical. A hacked email account is serious. A hacked machine capable of lifting heavy objects is something else. The labor question. The public question surrounding humanoid robots is usually immediate. Will they take our jobs? But that question is too broad to be useful. Technologies rarely replace work all at once. They alter tasks. A job contains many activities. Some are routine, some require judgment, some require physical skill, some depend on social trust, some are easy to automate, others are not. Humanoid robots carry parts while a human handles quality problems. It may perform dangerous inspections while a worker interprets the results. It may work overnight but require technicians during the day. It may eliminate one role while creating others in maintenance, supervision, integration, and data operations. The effects will vary by occupation, industry, and region. But humanoids could eventually matter in a way earlier automation did not. Traditional industrial robots are usually fixed and specialized. Their economic effect remains concentrated in particular manufacturing tasks. A flexible machine capable of learning many physical activities could spread across a much wider range of work. Warehouses, hotel, hospitals, retail, construction, agriculture, elderly care, home assistance. That is the long-term promise. It is also a long-term concern. The risk is not merely unemployment. It is bargaining power. If companies can rapidly substitute machines for workers during labor disputes or shortages, the balance between labor and capital could change. If robots remain expensive and concentrated among large corporations, automation could increase the advantages of scale. If machines become affordable to small businesses, they could distribute productivity more broadly. The technology does not determine the outcome by itself. Ownership matters. Tax policy matters. Competition matters. Training matters. Labor law matters. And the speed of adoption matters. A society can adapt to gradual change. Why humans want the robot to look human? There is also a psychological layer. Humanoid robots may be mechanically convenient because our environments were built for people. But the human shape also serves a cultural purpose. We understand it. A machine with eyes appears attentive. A machine with hands appears capable. A machine that nods appears cooperative. Designers may use those cues to make robots easier to interact with, but human appearance can create false expectations. A robot may look socially aware without understanding social meaning. It may speak fluently while lacking common sense. It may appear confident while operating under uncertainty. People may trust it more because it resembles a person, or fear it more for the same reason. This creates an unusual design dilemma. Make the robot too mechanical, and people may struggle to communicate with it. Make it too human, and people may attribute abilities it does not possess. The challenge is not merely engineering motion, it is collaborating trust. A useful machine should communicate what it knows, what it does not know, what it needs help with, and when a person should stay away. In a factory, this may involve lights, sounds, and clear motion. In home or care environments, it may become much more difficult. What happens when a child treats a robot as a friend? When an older adult becomes emotionally dependent on it? When a company records intimate interactions to improve the system? When the robot simulates empathy because simulated empathy increases customer retention. The body turns an AI system into a social presence. And social presence creates responsibilities software has barely begun to confront. What would count as success? Imagine a humanoid robot that performs one warehouse task for 8 hours. Is that success? What if human intervenes twice, 10 times, 50 times? What if the robot completes the task more slowly than a worker but never suffers an injury? What if it becomes economically only after operating for 3 years? What if it works well in one building but cannot transfer to another? What if the software improves continuously but the hardware wears out? Robotics needs standards of evidence clearer than viral videos. A serious evaluation would include task completion rate, failure frequency, human intervention rate, mean time between failures, maintenance hours, energy use, cycle time, safety incidents, deployment duration, generalized to change conditions, a full cost per successful action, and full cost per successful action. Without such measures, the public cannot distinguish progress from performance. This does not mean every company must reveal proprietary information. It means extraordinary economic claims requires operational evidence. The question is not whether humanoid robots can work. Some already perform real tasks. The question is whether they can do so reliably, repeatedly, and affordably enough to become a major labor technology. That question remains open. Possible futures. There are at least 3 plausible paths. The socialist future. Humanoid robots become useful in a limited range of structured environments, factories, warehouses, laboratories, hazardous facilities. They perform repeated materials handling and inspection tasks. Most remain closely supervised. Traditional industrial automation continues to dominate where specialization is possible. The humanoid becomes an important machine category, but not a universal worker. In this future, the technology succeeds without fulfilling its most dramatic promise, the generalization future. Physical world models improve rapidly. Simulation produces increasing transferable skills. Robots learn from human demonstrations and from one another. A skill learned in one facility can be adapted to another. Hardware costs fall. Reliability improves. One machine can perform dozens of tasks. Humanoids begin spreading from factories into logistics, service care, and homes. In this future, embodied AI becomes as consequential as personal computers or automobiles. The robot is not merely a machine, it becomes a general platform for physical labor. The distribution future. The economics fail. Maintenance remains too expensive. Battery life remains inadequate. Robots cannot handle enough edge cases. Serious accidents trigger regulatory intervention. Cybersecurity failure damage public trust, or specialized machines remain cheaper and more reliable for almost every important task. Investment declines, many manufacturers disappear. Humanoids survive in research, entertainment, and niche applications. In this future, the 2020s are remembered as a period when impressive motion was mistaken for general intelligence. None of these scenarios is certain. The evidence will emerge through actual operation, not promises, not fear, not promotional videos. Uptime, cost, safety, adaptation, and useful work. The body changes the question. Return to the robot on the stage. It turns, it walks, it raises its arms. At the beginning, we asked whether the movement was real. Now that question seems almost too small, the movement is real. The engineering is real. The investment is real. The factories are real. The regulatory conflict is real. But the meaning remains unsettled because intelligence changes when it enters a body. A language model can describe how to lift an object. A robot must feel the object's weight through sensors and motors. An AI system can suggest a plan. A body must survive the consequences. A chatbot can apologize for an error. A machine moving through a hospital, factory, or home must avoid causing an error in the first place. Embodied intelligence is therefore not simply artificial intelligence with legs. It is a different relationship between intelligence and reality. The world pushes back. Gravity votes. Friction votes. Human unpredictability votes. Every action becomes an experiment with consequences. That may be why the transition matters so much. For years, AI has changed information work, writing, research, programming, images, analysis. When AI acquires a reliable body, it begins competing with the physical economy. Not only with other software, with machines' infrastructure and human labor. The robot shape may be familiar. The system forming around it is not. It connects language models to motors, factories to data sets, workers to remote operators, national security to supply chains, human trust to machine behavior, and the oldest human economic question, who performs the work, to the one of the newest technologies on Earth. The next time you see a humanoid robot dance, notice what the video does not show. The training data, the failed attempts, the human operator, the maintenance crew, the battery, the supply chain, the security system, the business model, the workers whose tasks are being studied, the investors waiting for a scale, and the machine's first encounter with something its developers never predicted. That is where the future will be decided. Not in the perfect demonstration, in the unexpected moment afterward. When the box is damaged, the floor is wet, the tool is missing, the network goes down, a human steps in the way, and the robot must decide what physical world requires. So what evidence would change your thinking? Would 1,000 factory pilots convince you? Or would you need multi-year operating data? How much human intervention can occur before autonomy becomes misleading? Should companies disclose when a robot is teleoperated? Who owns the physical world? Data collected in a workplace and in homes. Should foreign-made robots face special security restrictions? How should workers share in productivity created by robotic labor? And if a machine can eventually perform the physical work of a person, what obligations do owners of that machine have to the society whose jobs, buildings, and accumulated human knowledge made it possible? When AI gets a body, it does not merely become more capable. It becomes accountable to reality. And so do we. If today's episode made you think, don't stop there. Read the research, study history, examine original documents, listen to the experts, listen to the critics, listen to people who disagree with you, question the sensational claims, question the official explanations, question the headlines, question the experts, question your assumptions, and question mine. Because Rabbit Holes Deep Dives is not about handing you conclusions. It's about following the evidence, even when the evidence leads somewhere uncomfortable. What evidence changed your thinking? Which claim deserves more investigation? What did we miss? Which assumptions should we challenge next? And what rabbit hole should we go down next? Share this episode with someone willing to examine the evidence. Join the conversation. Challenge ideas respectfully. Keep asking questions, because every answer opens another question, and every question leads further down the rabbit hole. Put it in the comments below. I read every single one. My name is Leroy Nellis, and this is Resilience Radio. Godspeed, stand for the Constitution, and never surrender your ability to think for yourself. God bless, and good night. Hey, everybody. I wanted to sit down with you today and talk about something we've been working on behind the scenes for quite a while now. First, I want to thank you. Whether you've been here from the beginning or you just found the channel recently, I want you to know that I genuinely appreciate every single one of you. Every comment, every conversation, every suggestion, every word of encouragement has helped shape what Resilience Radio is becoming. This isn't just my channel anymore. It's about a community. And because of that, I wanted you to hear these changes directly from me. Over the last several months, we've been doing something a little unusual. We've been studying our analytics almost obsessively. Not just YouTube analytics, but the analytics coming from Naomi, the AI production system we've been building from the ground up. We've been asking questions like, what videos do people come here for? What keeps people watching? What topics naturally fit together? And what happens when we mix very little types of content on the same channel? After looking at thousands of data points, we came to one conclusion. It's time to let each series become a very best version of itself. So today, I'm excited to announce that Rabbit Holes is becoming its own dedicated YouTube channel. Rabbit Holes deserves its own home. It's where we dive into mysteries, history, unsolved questions, and rabbit holes. strange events, forgotten stories, and all of those fascinating topics that make us lose track of time. By giving Rabbit Holes its own channel, YouTube can better understand who those videos are for. Our AI can learn from much cleaner data, and we can build something truly special for people who love those deep dives. Resilience Radio will continue doing what it has always meant to do: help people understand themselves through psychology.
You pushed me down, thought I'd stay on the ground, counting me out like the numbers didn't matter. But pressure builds diamonds in the dark, and I've been sharpening my edge in the chatter. Every scar turned into strategy, every setback fueled my clarity. I took the hits, learned the game, turned my losses into flame. Now I'm coming back strong, and you'll remember my name. I'm rising through the fire.